Hey, this is Brock Lemires, and in this video I'm going to talk about predicting the behavior of circuits that consist of resistors in series. And specifically we're going to talk about equivalent resistance of series resistors and also using voltage divider relationships to predict the voltage across resistors in series. So let's take a quick review of some of the kind of shortcuts that we've come up with using Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law. The first one is that we have derived that if you have a series configuration of resistors, the current through all of them is the same, which is kind of obvious when you look at the picture, but the equivalent resistance of them is just simply the summation of all the resistances, okay? But importantly, what does it mean to be an equivalent resistor? It basically means that you could replace these three resistors in series with an equivalent single resistor for all the analysis that you do. So for example, if you had a voltage across these three resistors, you would have a current that flowed through them. But if you put that same voltage across its equivalent resistance, the same current would flow through it. So it's kind of a shortcut to really to quickly analyze circuits as opposed to going back and writing full KVL, KCL equations. Another thing that we've looked at is the voltage divider expressions. So these were derived using KVL and KCL and Ohm's law again, but we came up with this shorthand way of saying if you ever have a series combination of resistors and you have a voltage across all three, you can quickly find the voltage across any of these resistors using an expression that takes the voltage across the three resistors or the series combination of resistors, and you multiply it by the resistance of the resistor you care about that you're trying to find the voltage across over the sum of the resistances in the series configuration. So for example, if I wanted to find V1 in this circuit, I could simply multiply Vs by R1 over R1, R2, R3. If I wanted to find V2, I'd simply multiply Vs by R2 over R1 plus R2, R3 plus R3. And if I wanted to find V3, I would simply multiply Vs by R3 over R1, R2, and R3. And again, all of these were derived using KVL and KCL. So let's go ahead and see how this works. So what I want to do is I have this circuit and I want to kind of figure out things about it. Okay, so what I want to do is I want to calculate everything that I would ever want to know about this circuit, and I want to do it with real values so that I can actually measure and verify what I'm doing. Okay, so what I've done is I created this table and it has the nominal values that I want to use for my circuit. So I have, Vs is going to be a 9-volt supply, and that's obviously going to come from a 9-volt battery. So here's my breadboard right here. So I got my breadboard and I'm going to power this little resistive circuit with a 9-volt battery, and so that's where the 9 comes from for the Vs. And then I'm going to have three resistors in series, and so I'll do R1 is 150 ohms, R2 is 150 ohms, and R3 is 1k ohm. Okay, and so I have those three resistors. Basically, I have those three right here, and I'm ready to go. But I'm going to calculate a whole bunch of stuff. Okay, but since I want to measure it, okay, I don't want to use these values because when I go to measure these with the multimeter, I'm not going to be close to these, or I might be close, but I'm not going to be very accurate because we all know that when you say 9-volt battery, that doesn't mean that this battery is exactly 9 volts. And the same thing with 150 ohms. When I say 150 ohms, it doesn't mean that this resistor is exactly 150 ohms. It's going to be some value that's within its tolerance. So I want to the first step that I want to do is I want to actually go in and measure these circuits or measure these components and get their measured value before I actually go and do any calculations. Okay, so let's go ahead and do it. So let's go ahead and bring out old trusty. There's a couple things to remember on this that are important. First of all, it's important to know that you want to measure the resistors individually without being connected to the voltage source. And that's because they need to be isolated by themselves in order to get the true value. If you try to measure them when they're in a circuit, you'll be measuring kind of the equivalent resistance all throughout the circuit. So I'm going to come out here and I'm going to take my first 150 ohmer and I'll go ahead and put this into resistance measuring mode, and I'll go ahead and clip onto this, and what I'll get is 148.7. So not too bad. 148.7. So that's 148 point, we'll give it 6. Okay, all right, so I got that recorded, and I want to make sure I remember that one. So I'm going to put it over here. So that's going to be R1 right there. So I got R1 is sitting right there. And now what I want to do is let's go and get R2. Okay, so let's get our next 150 ohmer, and I'll go ahead and clip onto that. And what I end up getting is 149.3. So I get 149. Well, it's going down 0.1. Let's give it that. Okay, and I want to make sure that I remember that little buddy right there. So that's R2. And then finally I got my 1K. So I'm going to grab that, and I go ahead and grab this, and I got to change my multimeter to measure up to 1K, and I get 988. Okay, so I get 988. All right, so now I want to measure the voltage. But remember, batteries, their voltage drops the more current you draw out of them. So I have to actually have the circuit itself built in order to know what voltage I'm going to have. So this is circuit analysis, right? So I know what I have. And so what I'm going to do is I'm going to keep these 150 ohms straight. And what I'm going to do is I'm going to come down here and I'm going to build this circuit. Okay, so I'm going to go ahead. These are going to be in series. So I'm going to pop that into there, that into there. And those are now in terminal strips. And then I'm going to take my second 150 ohmer, and I'm going to go, I'll push them over so you can see it. And I'll put that like there to there. Okay, so now I got the two in series. And now I'm going to do my third one, and that's going to be my 1K. I'm going to come down here, and I'm going to do boom. I'm going to go boom. And now I have my 3 in series. And now what I can simply do is I can just plug in my battery that's going to power my rails, and then all I'll do now is I'll just jump her over from this rail into this guy, and I'll go ahead and then grab ground, which was already there. I'll go into this rail. Actually, that wire's too short, so I got to go from here to here. Okay, so now that this thing is active, and so there's current flowing. So now what I want to do is I want to come back in and measure the voltage across the entire thing. So I can go ahead and tie in on the top right there, and let me make sure I'm in voltage before I do anything. So up to there, backlight, I don't know if that helps. Okay, so, and what do I get? I get 8.89, okay? So 8.89. So now I come down here and I got 8.89. So now those are the values that I can actually use when I do calculations. Okay, so that's my circuit. Let's go ahead and put that aside for a second. And now let's do some calculations. So now what we can do is we can actually do some calculations for, let's see, we're going to do some calculations to figure out these next values. So what I want to do here is REQ. So what is REQ? Well, REQ of a series combination is simply R1 plus R2 plus R3, which in this case was 148.6 plus 149.1 plus 988, and that is equal to, grab a little reliable here. So let's grab our calculator. Boom, 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 boom. So here I am. I got 148.6 plus 149.1 plus 988, and the answer is 1285.7 ohms. Okay, so that right there is my answer. So I can come in here and I can say, what is REQ calculated? It's 1285.7 ohms. Okay, and so this is volts, this is ohms, ohms, ohms. Okay, so I did it. All right, that one was pretty simple. Let's go ahead and do this now. Let's calculate V1, V2, and V3 using a resistive divider or a voltage divider expression. So what I can do is I can say V1 is equal to Vs over R1 over R1 plus R2 plus R3. And so that's my expression that I'm going to use to find the voltage on V1. Well, all I got to do is plug in these values now. So what was Vs? Well, the measured one I have is 8.89 multiplied by, and now we got R1, which is 148.6 over the sum of these, R1 plus R2 plus R3. Well, if you're okay, I'm just going to use this value right here because we already calculated it. So it's actually over 1285.7. Okay, and that'll make it a little bit easier to calculate. Okay, so here we go. So I got my calculator and I'm going to do this. I'm going to go 148.6 divided by 1285.7, and I say equals, and I multiply that by 8.89, and V1 should come out to be 1.027 or 28 volts. Okay, so that's my answer, and that's what I'm going to enter into my little table right here. So 1.028 volts. Okay, let's do the same thing for V2. Okay, so in this situation, V2 is equal to Vs multiplied by R2 over R1 plus R2 plus R3. And again, we're going to do the exact same thing where we say 8.89 multiplied by 149.1 over R1 plus R2 plus R3, which is 1285.7 ohms. And this should be very similar to V1 since it should be, they're trying to be the same resistor. So here I go. I'm going to take 149.1 divided by 1285.7 equals, and multiply by 8.89. And what I get is pretty much the same thing, 1.031, we'll say volts. So that's this guy right here. So 1.031 volts. And you can tell you need to be sort of careful when you do this stuff because it's pretty easy to make a typo or write something down wrong. And I keep bumping my camera. So here we go. Okay, V2. V3 is going to be equal to Vs over R3 over R1 plus R2 plus R3. And what is R3? We have 8.89 multiplied by 988 over R1 plus R2 plus R3, which we know by now is 1285.7. And this should be the rest of my voltage. So here we go. I'm going to take 988 divided by 1285.7 equals, and I'm going to multiply that by 8.89 equals. And I should get 6.83, we'll call it 2. And that's volts. So that comes in right here, 6.832 volts. And if I did a quick check on this, this should equal, if I added these three voltages together, it should equal 8.89. So let's do that really quick, just as a crazy check. So we'll go plus 1.031 plus 1.028. And it comes out to be 8.89. So 8.89. Okay, so that's like verifies Kirchhoff's voltage law. Not that we were doing that. Okay, now we want to calculate the current. So the current flowing in this circuit, though, this is kind of why we use the equivalent resistance, because I know that I have plus or minus 8.89 on here, and I want to make sure, the way I can calculate the current is I can actually use the equivalent resistance. So REQ is equal to 1285.7 ohms. Well, geez, I can just do Ohm's law in this very simple circuit and figure out what the current is. And so I can calculate it. So all I do is say V is equal to IR, and my voltage is 8.89. My current is what I'm solving for, and my resistance is 1285.7. And all I do is divide both sides by 1285.7, and I get my current. And let's see, I already got 8.89 over there, so let's just divide it by 1285.7, and I should see something like 0.0069 amps, which is going to be about, we'll call it 6.9 milliamps. Okay, so that number right there completes my table of 6.9 milliamps. Now the key is this. What if I went in and measured all this stuff? Would I even come close? So let's verify that this all works. One thing to note is that if you keep your battery plugged in, it might be getting drained. So I had unplugged the battery off camera right there. But let me go back and let's power this buddy up. And what do I want to do first? So if I look at my table, let's see, I want to measure REQ. Let's do REQ first. So REQ, I can't have the power supply connected. So I'm just going to unconnect the power supply from this, and I'm just going to come back in, and I'm going to put this in resistive mode. So I know it should be below 2000, but all I'm going to do is with those resistors disconnected, I'm just going to clip on and I'm going to go ahead and go across all three of them in series. And the answer I get is 1287. Okay, 1287. So that's what I measured, 1287. Now let's go enter that into the table. So 1287. So I come down here and I get 1287. Well, how close am I? Well, it was 12857. Well, round that up to be 1.86. So I'm within an ohm. Okay, so I'm not just within 10%. I'm within like 1%. I'm really, really close to that. So my calculations were really good. And life is good. And why would there ever be an error? Well, it's because of the significant figures on here. So I'm kind of just like going really fast and saying 8, 9. Well, if I take these significant figures out more, I would get more accurate. In addition to the voltmeter doesn't have accuracy that's exact either. So there's sources of error in here which are just, we just know. Okay. All right. So now let's do the voltages. This one will be fun because let's power this buddy up. So now I got my power on there and I got my circuit right here. Let's see. I want to make sure I got everything on the screen. So I got resistor, resistor, resistor. I'll go ahead and add my power back in, add my ground back in. And now now I'm good to go. So let's bring old Trusty up here and put him on. I want DC voltage. And these are going to be, this is 2 volts, so I should be able to measure voltage across the first couple buddies. So here's V1. So I'm going to go ahead and grab V1 right there. And the answer comes out to be, well, I did it. Let me put the black terminal on the down and the red terminal on the up, and I'll get my number. So I've got 10, that's millivolts. Let me push it up to 20 and see what I get. I get 1.02. So now if I come up to my table, what do I have? 1.02 volts. And that one's right on. Okay, so that one's like perfect since you can't see the significant figures. If I went over to here, I would actually see this is like saying it's 1022 millivolts, which is the same as saying 1.023 millivolts. And why is that even different than that? Well, the battery could be draining. There's sources of error in here, but look at how close I am. I mean, I'm within 10% easily. Okay, so let's do the next one. So let's go down to, let's slide down and do our V2. So now I got V2. So I'm going to come in here, go ahead and clip onto this buddy right there, and I'll clip onto this buddy. And what do I got? Well, once again, I come out there. Oh, I got everything. You got to make sure these leads don't touch everything. And I get 1.01. Okay, so let's see how close I am there. 1.01. Hey, pretty dang close. I mean, we're within a couple percent. Life is good. And again, the battery could be dropping. And so let's go ahead and get V3. And there I go. And I end up with 6.74. So let's put that in there. So 6.74. It's like, wow, this is pretty cool. The voltage divider thing really did work. And if I go back and check what's happening with my battery, look at how much my battery's dropped just since I started this circuit. 8.79, and we started with 8.89. So that's, the more I run off this battery, the more it's dropping. And so it's introducing more and more error over time. But we are getting within very close of the answer that we calculated using our voltage divider and equivalent resistance just by using these shorthands that we came up with. And look how close I am. So now let's do the final measurement. So now I'm going to go into current mode. So I'm going to be measuring current, and I'm going to come down here to current. And I know it's less than 20 milliamps. So I put it into 20 milliamps. And what I want to do is I'm just going to break the circuit. So I go ahead and do this, and I'll go ahead and pick up here, and I'll pick up there, and let's see what I get. So I clip on, and I end up with 6.73 milliamps. Okay, 6.73 milliamps. So I come over here and I get 6.73 milliamps. And look at that. So let's recap what we did. We first of all, we had a simple circuit and we measured the actual values so that we could calculate stuff, but we used these shorthand kind of shortcuts that we derived originally from KVL and KCL and Ohm's law, where we could combine series resistors. We could use a voltage divider to find the voltage across resistors in a series configuration. And then we used the series or the equivalent resistance to actually find the current through all of them. And it was actually pretty dang fast. So this is like in 20 minutes, I was able to calculate all these things without without having to write full-blown KVL, KCL across the whole circuit. I just used the shortcuts. And then I verified using measurements that this absolutely, in fact, does work. Okay, so that's how you can use these things to evaluate resistors in series and voltage dividers. All right, that's it, and see ya.